Welcome back to our ongoing discussion on parametric equations. Last time we introduced what it was to be a parametric equation, how it wasn't quite a function but rather a combination of functions. And what we're going to do today is start to graph a few. Do a few examples and then we will wrap things up. So picking up from last time, we have a few basic strategies when it comes to graphing a parametric equation, which is a pair of functions really. One for x as a function in t, the other for y as a function in t. Just list your values for t in ascending order. So if you want to go from negative infinity to infinity, you just say -5, -3, -1, 0, 1, 3, 5, and you just go down for t accordingly. And then for each value of t, solve for x and y as you go. And then, as we had done before, we pull out all of those points in order and use arrows to go between point to point. Also, as I mentioned towards the end of the last video, if we can, and if it helps, we can try and eliminate the parameter t and just have some single function. And that would be helpful, as we'll show here in a second, as far as how the graph might look. And then lastly, when you are finally done, when you're considering that you've plotted enough points, and we're confident that we have plotted enough points, we'll just draw the rest. And that's our goal. That's what we're going to do here. So first example, I want to graph the parametric equations determined by x equaling 2t plus 1 and y equaling t plus 1/2 quantity squared. Now you can make a table of values for this, and we will in the next slide. But first of all, check and see if you can eliminate the parameter. Man, I can't pronounce tonight. Check and see if you can eliminate the parameter and use that single curve to see what your parametric curve should look like. So for this, I recognize that I've got some very similar arguments here, right? 2t plus 1, if I were to cut that in half, I would get t plus 1/2. So I do exactly that. I divide my first equation by 2. Giving me x over 2 is equal to t plus 1/2. Well, this t plus 1/2 pops up in the equation for y. So instead of t plus 1/2, I can just write x over 2, which does square out to be x squared over 4. So this parametric equation, what this is describing is actually a parabola, x squared over 4. Now, I know if you're keeping score, you'll recognize that we had a parabola last time and a parabola this time. No, not everything is a parabola. But it does fairly often work out to be either a linear equation or a parabolic equation, especially when you're starting out with some of the simpler equations here. So we know at the end of the day we should have a parabola. And now we're going to try and work to make sure we get that. So I'm going to make a list of values here for t, starting with the usual suspects from -2, -1, 0, 1, 2. And actually, as we'll see here, that's not going to be good enough. But just starting with these 5, right? If I were to put -2 in for t, for x, that's going to be -4 plus 1. That's -3. Put -2 in for t, for y, that's going to be -2 plus 1/2. That's -3/2, which squares out to be positive 9/4, 2.25. And then doing it for -1, that goes into the x equation, so that's going to be -2 plus 1, that's -1. And then -1 goes in here for the y equation, and that should end up giving you 1/4. And you can keep going. Make sure I'm right on this. Take a moment, pause the video, make sure I got all these points right. And those are our 5 points. Now I want us to know right now, this is not the only 5 points worth plotting. In fact, if you just plotted only these 5 points, you would run into just as much trouble as you would have run into in the algebra side of pre-calc if you just plotted 5 points for any function. You're going to miss a lot of information. And let me back that claim up. So here is my 5 points. Right, the same 5 points we had here, right? -3, 2.25, -1, 0.25, and so on and so on. That is my 5 points. Well, let's say I were to bust out my pen and just draw those 5 points. So let's see, I started here, right? This was my first point. I went here. and then I go straight over here. And then I go up here. And then I go up here. Now we can kind of deduce that this is a parabola, but at the same time, does this vertex end up being exactly here? Does it go further down? Does it do some weird nonsense in between? I just don't know. I haven't plotted enough points to know for sure. In fact, if you wanted to know what this spot is exactly here, you would have to use t equal to a half, I believe. No, negative a half. Negative 0.5 would be the t value that you would need to get the vertex at 0, 0. And with just these 5 points, we haven't done enough to know that. We would have to plot still more. Alternatively, we could recognize that, oh yeah, my plane curve, if I use just the rectangular coordinate equation, is the parabola here. And so now, I don't need to worry about that. Instead of all this, confusion and mess, I can say, oh yeah, this is my curve. Here's my arrows. Here's my arrows. Here's my arrows. And I'm really bad at drawing them with a mouse, but you get the idea. There's my arrows. So that denotes the direction we're moving in, which is a combination of two things now. It's a combination of our plane curve generated by the rectangular coordinates from eliminating the parameter, and also from plotting enough points to verify the direction we're moving in. And yeah, this is correct. We can check that by using the polar plots and making sure that as z moves, or this is a placeholder, right, as t increases, that we are moving from left to right. And we do have it. We did get there. We got it. All right, one down, one to go. Let's see here. I have another example. So I also want us to look at here. I want us to look at the parametric equations y equaling cosine squared t, x equals sine squared t, which seems rather innocent enough, right? If you wanted to eliminate the parameter on this one, well, sine squared plus cosine squared is always 1. So that means, well, sine squared t plus cosine squared t is 1. Well, that's x, that's y. So really, my coordinate equation is just x plus y equals to 1. Well, x plus y equals 1. Okay, it's just a linear equation. Thanks, Fat Goat. I need to go offline on my Steam account here. Whoops. Anyway, right, so I think, based on my elimination of my parameter, that I need to have some linear equation like this. Well, let's see. Let's plot a few points. And by plotting a few points, I mean plotting a lot of points. Because I'm looking at oscillation here. I'm looking at sine squared and cosine squared. I'm looking at trig equations. I need to use all the nice values that I can. And interestingly enough, we'll see what happens is as we go around, and you're going to want to, again, stop and think about this for a minute. When t is 0, sine squared is 0, cosine squared is 1. At t is pi over 6, sine squared is a fourth, right? Because sine of pi over 6 is a half, that squares to a fourth. Cosine of pi over 6 is root 3 over 2, squares to be 3 over 4. And curiously enough, what happens is my x-coordinate goes from 0, steadily up to 1, linearly up to 1, and then linearly back down to 0. And if we were to keep going, back up to 1, back down to 0. Similarly for the y's, it starts at 1, goes down, then back up, and then down, then back up. Also, a little note, right? If sine squared had been 0.9, then y would have to be 0.1. It looks like all the values I'm going to have for this thing isn't all of this stuff, but rather just everything between 0 and 1. Is that right? And indeed it is. You see, if you were to plot those points we had, all your points would be on just this single line segment right here. And if you were to draw them in order and trace them in order, you would have your points move up and down, back and forth, all the way forever. And so the way you would denote that traditionally, to say you were going bidirectional, let me try that a little better. You usually draw two arrows, kind of like an equilibrium for those of you with chemistry under your belts. You have half an arrow going one way, half the other going the other way. And that's how you would denote the bidirectionality, I guess, the fact that you're going back and forth in both directions. So let's take stock here. How does that stack up to this, right? What we originally guessed. That coincides, but this is radically different than just a straight line. This has oscillation to it. And the takeaway I want you to make from here is elimination of the parameter is great, except when you have oscillations. And then all bets are off. You've really got to be careful there. And so that's where you just have to really, really carefully plot a whole lot of points and see just how much of the curve is actually being generated and just how much of it is going back and forth and in one direction. Maybe it's both, maybe it's in one. Just a lot to consider. And seeing as how this is a survey course, survey in parametric equations, unfortunately that's about all we have time to do here. Right? There is a lot more that could be said about parametric equations, but we really ran out of semester. We ran out of time. There's too much to do. This is so secondary to everything else we have to do. It just comes as an afterthought. And that's kind of sad, but kind of necessary too. So that's it for now. We'll have one last final video where we tie everything up. I'll see you then.